Greetings, students. Mr. Harrison here from school. I wanted to talk to you today about our slideshow on matter, what it is, and why it matters. See what I did there? All right. Matter is anything that has mass and volume. And remember, the definition of volume is how much space an object takes up. So matter is anything that has mass and also takes up space. Everything that we know of in the world physically is made up of matter, and all matter is made up of tiny little particles that we call atoms. And also these particles can be arranged in different ways, and the motion can change of the particles. And because of that, matter can exist in a couple of main phases. There's actually 5 of them. We're going to focus on 3, but we're also going to include the 4th. The one we're not including is a very, very, very cold one called Bose-Einstein condensate. You don't need to know about that, but you can look it up if you're curious. So let's look into these various phases. The first and least energetic and also coldest phase is called solids. And I like to think of these things in terms of water. So solid water is called ice. So have like ice in the back of your mind as we go through this. Solids have particles that are tightly packed together. They're not very spread out. They do not move past one another, but they do vibrate in place. I apologize because we had an animation here with these particles, but it's not working on the slideshow and there's no way to fix it. So just imagine, if you will, that these particles are vibrating and they're bouncing off of each other, but they're keeping their shape. So they're kind of just like ricocheting off each other in their general area that each of them stays in. And that's what happens in a solid. Also, in a solid, the object has a definite shape. Another way I might say it is it's a fixed shape. In other words, their shape doesn't change. The shape remains what it is. They also have a definite volume or a fixed volume, which means the volume also doesn't change. So it keeps its shape and it keeps its volume. It occupies the same amount of space at all times. For example, think of a marble, as well as ice, obviously, but think of a marble. The marble is going to be shaped like a sphere, and it's going to stay the shape of a sphere no matter what happens, unless it breaks in half, which that's just cutting it in half. That's not actually changing its shape. And the volume can be found with a graduated cylinder using a method called water displacement method. But solids have fixed shape and fixed volume. Everything stays the way it is. Liquids, on the other hand, are a little more energetic. They're a little warmer than solids. So think of like liquid water. That's why we got the water cooler here. In liquids, the particles are still pretty tightly packed, but they're starting to spread out a little bit, and they move around more vigorously and can actually slide past one another. So if we could activate this little deal that's not working here in terms of animation, you'd see these particles kind of slipping around behind and in front of each other, but not moving really, really fast, just moving a little bit. Liquids do not have a definite shape because they take the shape of the container you put them in. When you pour water from one container to the next, it doesn't keep the shape of its original container. It takes the shape of its new container. And also liquids, although they don't have a definite or fixed shape, they do have a definite or fixed volume. So it's still going to take up the same amount of space. In other words, 1 liter of soda in the bottle is going to be the same as 1 liter of soda in a punch bowl or in a cup. It's still going to be 1 liter, but it's going to take the shape of that container you pour it into. For example, we've got orange juice. Because you pour it out of the carton into the juice glass, it still is the same amount of or space of volume of orange juice, but it takes a new shape because we pour it into a new container. And volume of this can be found using a graduated cylinder. Our next phase is gases. Gases have particles that are not tightly packed together and have so much energy that they slip past each other quickly and easily. So these particles here are spread out a little bit more. And if we could do the animation, they would be easily moving past one another and very quickly moving. So they're higher energy, higher movement, higher temperature than liquids and solids. And because of this, they do not have a definite or fixed shape. They have a variable shape. Remember, variable means changing. And they also do not have a definite or fixed volume. So their shape and their volume is changing all the time. Gases tend to spread out, which is kind of crazy. So they take up more space and they don't have a fixed volume. So they do take the shape of their container, much like liquids, but they also expand and contract. Smoke is an example of a gas. Shape isn't definite. Volume is also not definite or fixed. And they usually are expanding in general, unless they're cooled. So here's a couple laws that you need to know about gases. First one is Charles's law, and that states that the volume or the amount of space that a gas takes up and the temperature of that gas are related to one another. When the temperature of a gas goes up, so it gets hotter, the volume also goes up. So essentially, when we heat up a gas, it expands and takes up more space. Likewise, the opposite is true. When the temperature goes down or we cool down a gas, the volume also goes down. So as gases cool, they contract and take up less space. And we memorize that by saying up T, up V, which means as temperature rises, so does volume. And as temperature goes down, so does volume. This is a principle we use a lot for hot air balloons, because if the air balloon on the left side is kind of deflated, but we heat up the gas inside by blowing that little fire torch in there, then the gas will expand in the balloon, causing it to rise and be able to fly. But if you need to land, you just need to turn off the burner and the gas will gradually cool down, and then the balloon will deflate a little more, and it will take you nice and slow to the ground. Okay, another gas law that you need to know is called Boyle's law. Boyle's law states that the volume of a gas and the pressure of that gas are related. So it says that when the pressure goes up, the volume goes down, which kind of makes sense if you picture a balloon and you're squeezing the balloon. As you squeeze the balloon, the volume is going to go down. So you're putting more pressure on it. Pressure goes up, the volume goes down. It's going to take up less space. But likewise, when the pressure goes down and it's allowed to expand, the volume goes up, so it takes more space, which makes sense because we know that gases want to take up more space. And that is signified by up V, down P, which means as volume increases, pressure decreases. And we can use those things to artificially change the temperature of a gas, because if you go back a couple slides, as the volume goes up, so does the temperature, and as the volume goes down, so does the temperature. So combine that with this, that the pressure goes up, the volume goes down. If we increase the pressure of a gas, the volume is going to go down. And what happens to the temperature when the volume goes down? The temperature goes down. So we can artificially cool a gas by increasing the pressure on that gas and making the volume go down and therefore the temperature go down. And that's actually something we use that we'll talk about later in heat transfer when we talk about things like air conditioners and refrigerators and freezers, because they use pressure to artificially heat and cool the gas. Oops. All right. So low pressure to high pressure. As we move from low pressure to high pressure, then we move this way with the particles, and from small volume to large volume works the opposite way. So as we increase the pressure moving up to down, we're actually going to decrease the volume. But as we decrease the pressure, we're going to increase the volume. It's called an inverse relationship. When one goes down, the other one goes up, and when one goes up, the other one goes down. So last phase of matter. In this one, we have a lightning bolt because lightning is actually this phase of matter. It's called plasma. Remember, gases were pretty hot. Liquids are a little cooler. Solids are the coldest. Plasma is the most energetic, the most motion, the most energy, the hottest, the highest temperature. Particles in a plasma are moving so quickly that it's hard to even see what they're doing. So if we were to turn on this animation, these particles would be going everywhere on the page. It'd be hard to even keep track of them. So basically, to make a plasma, you take a gas and you give it even more energy, usually using electricity, and then you create a plasma. And like I said, lightning is an example of a plasma. So take a second here and go over this chart here. So we got solid, liquid, gas, plasma. Lowest energy, little higher energy, highest, little higher energy, highest. So as we move from solid to liquid to gas to plasma, we're increasing the energy each time. So it makes sense that the particle motion would increase each time because there's more energy. So as particles vibrate in place for a solid and they're heated up a little bit, it goes from slow to medium speed. The particles are still close, but they can slide past one another now, so it takes the shape of a container. Then we speed it up a little more when we got from medium to fast speed in a gas, and the particles are constantly expanding. So they're now no longer taking just the shape, but they're taking the shape of the container, but they're not keeping their constant volume. And then we take that gas and we speed it up even more, and we have faster motion than we can even see. Motion of the particles is almost unknown because it's so fast. So we're done. If you have any questions and you're a digital learner, please email me those questions. And if you're someone in person, now's the time to ask.